Okay. So we'll take up this numerical in the unlocked circuits. So we wish to analyze the transistor amplifier shown in the figure, which is this, to determine the voltage gain V0 by Vi. So this is V0 and this is Vi. So this quantity Vc and this quantity VBB, both are the DC values, the biasing values. Due to the biasing, whatever we have, only that is there over here, right? Otherwise, what we are interested is only this V0 by Vi given this circuit where RBB is given, VBB is also given, RC is given, VCC is given, and all that, right? So if you see this, the biasing part means you need to remove this Vi. If you remove this, then it will become just the biasing part, which is just, VBB connected to the 100 kilo ohms, and then you have this transistor and then this 3 kilo ohms and then all that. So now when we do that, then this, whatever values are calculated here, now this is only the, biasing or the DC equivalent circuit over here, biasing or the DC equivalent circuit. So this will be capital IB, this is capital IB, right? Similarly, this is capital IC. How we calculate, we'll come to it a little later. For the present, this is capital IC, this is capital IB, this is capital VC or VCE, because the emitter is grounded. You can see that the emitter is grounded in for both these cases. So either you write VC or VC, it hardly matters. Okay. So this 3.1 is referring to only this capital VC over here, right? And this 2.3 is capital IC, and this 0.023 is capital IB. So how do we analyze this whole thing is what we need to check, right? So were we given with something so that we can analyze this circuit is what we will try to see. So generally, whenever we have such a case and we put it like this, then we when 3 volts is there, we assume that this base to emitter junction is forward bias. So when the base to emitter junction is forward biased, then the voltage across the VBE is 0.7. That is what is shown here. Voltage across this VBE is 0.7. So when this is 0.7 and this is 3 volts, then the current through this is 3 minus 0.7 divided by 100 kilo ohms. 3 minus 0.7 by 100 kilo ohms is this capital value of IB. Potential difference divided by the resistance will give us the current flow. So IB, capital IB will be equal to 3 minus 0.7 by 100 kilo ohms, and that will give us 0.023 milliamperes. That will give us 0.023 milliamperes. So this is capital IB. If capital IB is this value, capital IC will be, given by the formula beta into capital IB, beta into capital IB. And beta is given over here as 100. So you multiply this by 100, you will get naturally 2.3 milliamperes. If you multiply this by 100, then you will get 2.3 milliamperes. Having got this as 2.3 milliamperes, we can find the voltage here. We can find the voltage here. And the voltage here will be 10 volts minus 2.3 milliamperes into 3 kilo ohms. So 10 volts minus the drop voltage across the 3 kilo ohms. Voltage across the 3 kilo ohms is 3 kilo ohms into 2.3. So 10 minus 2.3 into 3 will give us, the 2.3 into 3 will be 6.9. 10 minus 6.9 will be 3.1 volts. Okay, 3.1 volts. Now, because this is grounded, VCE value will be 3.1 volts. So 3.1 volts is quite a good amount of voltage. If the voltage here is, see, first we are telling that the base to emitter junction is forward biased. Base to emitter junction is forward biased because of the reason that you have a positive voltage. Further to that, the value here is here 3.1 volts, much more than the saturation value. VCE set, the VCE set value is generally considered, somewhere around 0.3 volts. So 0.3 volts, if this value is more than 0.3 volts and this is forward biased, we say that this transistor is in active mode or active region. Active mode or active region. If this value becomes 0.3, then it will no more be in the active region. Then at that time, we can't say capital IC is equal to beta capital IB. That cannot be said at all. That cannot be said at all. So this is all right. We are taking IC is equal to beta IB, and that gives us a value here which is more than the 0.3 volts, which is the saturated value. Therefore, it is still in the active region. Say, for example, if this value turns out to be such a value that 10 minus this quantity, 10 minus the voltage across this, turns out to be lesser than 0.3 volts, or might be sometimes negative volts, which is impossible. Negative volts, which is impossible. Then we should consider that this transistor is in saturation because this is forward biased. Okay, that's the very important point. At that time, IC will be lesser than the beta IB. IC will be, when it is in saturation, IC will be lesser than beta IB, whereas in active region, IC will be equal to beta IB. IC will be equal to beta IB. Right? So all that is being mentioned over here. So all that is analysis of the biasing circuit. We are just talking about the analysis of the biasing circuit, and that is nothing but fixing up the quiescent operating point. Quiescent operating point means the value of capital IC, which is 2.3 milliamperes, and the value of the VC or the VCE, whatever you call it, which is now here 3.1 volts. So Q point is referring to IC and VCE. IC is capital IC and capital VCE. Capital IC is this, capital VCE is this. That is the quiescent operating point. So we are fixing up the quiescent operating point over here. So all that is calculated here till this point, right? All that is calculated here till this point. So we are just fixing the operating point here. Okay, we have determined the operating point here. Now next what we do is we try to find out the value of RE, GM and RPI. RE is VT by IE. VT by IE. We know IC. IC we have found out here 2.3 milliamperes, right? IC we have found it as 2.3 milliamperes. So we can find IE. IE is nothing but IB, IC plus IB. IC plus IB. So IC is this, IB is this. You can add both these together, or you can write like this. I think it is better to add these two quantities, 2.3 and 0.023. That will give us 2.323. And that will be the value which will be there here in the denominator. He's calculating alpha and doing that. Not at all necessary. Not at all necessary. You can as well write over here the value which is sum of both these values. Okay, which is again same thing as this, right? 25 millivolts divided by 2.323 milliamperes. That will give us the value which is 10.8 ohms. Okay, then GM will be equal to IC by VT. VT is the volt thermal equivalent, which is equal to 25 millivolts, and IC is 2.3 milliamperes. So milli will cancel, and we will be left with 92 milliamperes per volt. Having found this, then RPI is beta by GM. You can write beta by GM here. Okay, you can write beta by GM here, or you can also write VT by IB. Both are same. VT by IB or beta by GM, both are same. Standard thing is, beta by GM is a standard formula most of the time which we use for RPI. So beta is 100, which is given to us over here, right? It is given as 100 over here, and here it is the value GM is 92 milliamperes per volt. So this is milli. This is a figure which is 100. This is milli. Therefore, this will become kilo ohms. Milli, if it goes to the numerator, it will become kilo. And this is resistance, hence it is kilo ohms, 1.09 kilo ohms. Okay, 1.0 kilo ohms. So now, having found this in the second step, what we do is we just short the voltage, DC voltage sources. DC voltage sources are what we have here: VBB and the VCC. So short this to ground. Okay, short this to ground. Then we will get this second. Okay, so we are left with only VI, and this is connected to ground, and this is shorted. So when we short this as well as the VCC, VCC is shorted means it's connected to ground. So thus we get the circuit which is something like this. Now we need to replace this transistor by the hybrid model, hybrid pi model. The hybrid pi model is substituted over here is like this. You can write here beta IB also, but okay, this is also all right. You can write beta IB, or you can write GMVB. Okay, beta IB or GMVB, both, either of the two you can always use, right? GMVB or beta IB. So we know the value of GM we have found out. So now this is grounded and this is grounded. So that means they are connected together. This is also connected together. So you have an input, loop, and also an output loop. Okay, you have an output loop and an input loop. This is the input loop and this is the output loop. So input loop current you can find out VI divided by 100 plus R pi. R pi we have found out to be 1.09, right? 1.09, and RBB we have found out to be 100 kilo ohms. So add both of them, 101.9. That will be the value, right? That will be the current which is flowing through that. VI divided by 101.09. Okay, 100 plus 1.09 is 101.09. That is the one which will come in the denominator for the current. That current, if you multiply by that value of the current, if you multiply by R pi, you will get VPE. You will get VPE, right? So that current is IB. IB into R pi will give us the value of VPE. Okay. So other way of writing just that is VI into R pi divided by RBB plus R pi, and that will be the value which is there. So, and that is what is found, over here, right? VI into 1.09 divided by 101.09, and that turns out to be 0.011 VI, 0.011 VI. So VBE is find out, but we have here GMVB as the current. So GM we have found multiplied by VB. So this is GM, and that is multiplied by VB, or you can find IB and multiply by the beta itself. Both are same. You will either way get the value of the GMVBE, GMVB, whatever value you get over here, and that is flowing like this. You can see that it is downward here, so naturally it will be upward here, current. So current will be flowing like this. Current will be flowing like this. So that this is a current source. Please remember that this is a dependent current source. This is a dependent current source, and that value is equal to GMVBE. So GM is calculated there, and then the 92 milliampere per volt, and the value of VB is 0.0011 into VI, both to be multiplied, and we'll get that current, that multiplied by the RC, because current is flowing like this. Okay, current is flowing like this from the ground upward, means minus of GMVB into RC, minus of GMVB into RC, and that is what we have written over here. So V0 is equal to minus GMVB by VB into RC. So GM is 92, VB is 0.011 VI, and RC is 3 kilo ohms. And we know very well that GM is 92 milli, and this value is straight away 0.011 over here. So milli and the kilo are going to cancel and we'll get here minus 3.04 VI. So VI you take this side, then you'll get AV is equal to V0 by VI is equal to minus 3.04. Thus, we get the amplification which is needed, V0 by VI. That is what is asked in the question, right? What is V0 by VI? That will be minus 3. So minus is only because of the reason that the current which is flowing here is downward. That current is naturally upward here because loop current will be like this, right? Loop current will be like this. So because the arrow is downward, the current will be upward here because loop current direction is like this. Okay. So thus we can find the value of the, AV. So is it clear? We'll go for the next problem if it is clear. If you have any doubts, you can ask in the whole of the problem. Yes. Anybody has any doubts in this numerical? We'll go for the next numerical, and that is an unsolved problem from the book. I'll not be solving this, but rather I'll be telling you have to take a pen and a paper and sit with it. Unless you don't sit, you can't find the solution for this. Please remember that. Okay. So I'll be telling the things, and you need to write it down and try to calculate. At least the formulas you try to write and calculate. Till then, it is not possible. Is it clear whatever I had told till now? Are you able to hear me? Get me? Or you are not able to hear me? Hello? Okay. So now we'll go to this problem. We'll assume that you have followed whatever I have told, because two people have written here understood, and nobody else is telling that they have not understood. So that I'll assume that everybody has understood the thing. Okay. So we'll go for this 6.86. Take a pen and a paper and a calculator and sit down so that you can find the value of this. Again, this will go into, I am telling orally, it will go to the assignment. I don't know how many people have submitted. We'll open the page today itself and check what is the situation, how many have submitted, right? So 6.86 is what we have. The NPN BJT with grounded emitter is operated with VBE equal to 0.700 volts. So this VBE is what? This VBE is what? Can somebody write in the chat what this VBE is? Yes. V is voltage. BE means base to emitter. And what is the quantity? Is it the DC value, or it is the AC value? It is the biasing value. What do you call it? When both of them are capital, what do you call that? So when both of them are the what you call capitals, it is known as either DC or biasing. You can call that as DC or biasing. Okay, you can use both the terms. Either you use the term DC or you use the term biasing. Okay, VBE. Okay, this VBE will be you can say we have another value here, VBE. This is the total voltage. Please remember that this is the total voltage, and this is the DC component or the biasing component. So you add this with the AC component, then you are going to get the value which is total, right? So this VB is 0.700 volts, at which the collector current, this is very much important, at which the collector current is 0.5 milliamperes. So when we say at which, then the collector current also is the DC value, capital IC. So this is VB equal to 0.7, you write down. Capital IC is equal to 0.5 milliamperes, and we have a 10 kilo ohm resistor which connects the collector to the 10 volt supply. A 10 kilo ohms collector resistor connected to the collector to a 10 volt supply. So grounded emitter. So that means we have the same circuit which we had, in this case. Okay, we have again the same circuit whatever we have here, right? We have the same circuit whatever we have here. So we need to consider, but we don't have RBB. We still don't have the RBB, only RC is given. RC is given, and emitter is grounded. Emitter is grounded, right? We are not given still the value of RBB in that problem. So what does he want? What is the resulting collector voltage VC? So this is the V is capital, C is capital. This Oh, it is closed. Oh, sorry. So, so I was just telling that we have here the VCC, VCC minus ICRC. VCC is 10 minus the value 0.5 milliampere multiplied by 10 kilo ohms. Okay, that will give us the value which is 5 volts. That will give here the value which is 5 volts. Okay, that will give the value which is 5 volts. So once having found that value of 5 volts for this VC or VCE, now if the signal applied to the base raises to VBE, raises VBE to 705 millivolts. So if you apply a signal, then the VBE becomes 705 millivolts. So capital VBE is zero point 0.7 volts, that is 700 millivolts. The small v with the capital V, this is the total voltage which is 705. Then definitely this minus this will give us the AC voltage. That is the signal amplitude VI. VI will be the signal amplitude, which is 705 minus 700 millivolts. You can write 705 and you can write 700 millivolts, or you can just write 0.705 millivolts and this has 0.7 volts. So totally the difference will be the value of small v with a small be or small vi will be equal to 0.005 millivolt. 0.005 millivolt. So 0.005 millivolt will just turn out to be, might be 5 microvolts. Okay. we can just write 0.005 millivolts. That is the input value. So for that value of the small v with a small be, find the resulting total collector current IC. This is the total collector current. When we say total collector current, please remember that it is the sum of the DC as well as the AC. Okay, and the total collector voltage we see again, this is the sum of the DC plus the AC. Okay, so biasing plus the signal due to the input value. So using the exponential IC-VB relationship, he wants us to use the exponential IC and VB relationship. So what is the exponential IC and VB relationship? It is this. It is this. Okay. So what does he want us to find? He wants us to find the value of IC. The value of IC. How do you find that? We need to use this. IC is equal to IS e to the power VBE by VT. That is IS e to the power of VBE. So this is total value. Because this is total, this is also total value. So that total value is separated out into DC and AC, and we are separating that out. And this value, okay, that value is the DC value of DC collector current. This is IC, and that is what we have here. So we have this equation. Either you can write it and you can write this, or you can write this directly. IC is equal to, this is small I capital C is equal to capital I capital C into e to the power of VB by VT. So this is known to us 0.005 we have found out millivolts, 0.005 millivolts. This is 25 millivolts. This is E again. IC is also calculated, IC is given to us rather as 0.5 milliampere, and hence we can find out the value of the the value of this IC. Having found this IC, you can find the value of the VC. Okay, capital V, small v capital C. Small v capital C is again VCC minus this IC into RC. IC we have found from that equation, and then VC will be VCC minus this IC into RC. Because this is total voltage, we should use the total current for that. VC is equal to, okay, that VC is equal to, we can, I think we can go back to that figure, right? VC is equal to, this is the total voltage here, VCE is equal to VCC minus this IC into RC. VCE or V with a capital C, both are same. This value is what we are trying to find. That is VCC minus this IC into RC. This IC we have just found. You can multiply and get it, right? So having found that, then for this situation, what are VBE and VC? VBE we know, VBE we have found 0.005. VC will be this VC divided by the VC which we have found. The VC which we have found is 5 volts. Okay, capital V, capital C is 5 volts. Okay, capital V, capital C is 5 volts. That should be subtracted from whatever value we have got here. This will be definitely more than 5 volts because this current would have increased from the capital value of IC. So definitely you will have that value, and I think VC might become negative here. Okay, so this VC will become negative here, right? This value of VC will become negative here because that is a common emitter configuration. Okay, you can find that value of VC. So having found the value of VC, you can find VC by VB, which will be again a negative value. VB is 0.005. VC we have found out here and calculate that. Now compare this with the value obtained by minus GM RC. GM we have, you can calculate. The GM can be calculated as, GM value is IC by VT. IC we know 0.5 milliamperes. VT is 25 millivolts, then you can just try to find the value of GM. RC is given to us as 10 kilo ohms, and compare those two values. Okay, this value and this value, because this is approximate, and this is the accurate, because we have taken the exponential relationship between IC and VB. Here we are just trying to approximate this exponential relation by means of the so to say, only few of the components. First two components we are taking, we are not taking all the components together, right? So that can be seen by just going back. That can be seen by just going back to the figure